Hi everybody, here's the supplemental video lecture on IR spectroscopy. I know we've covered IR in lab quite a bit already, but I wanted to have a little bit of review before we go into other areas of spectroscopy. So the general idea behind spectroscopy is that it's the study of how electromagnetic radiation interacts with matter. It's a study of how electromagnetic radiation, which is just a fancy word for really saying light, interacts with matter. And we've got a couple equations that are really useful here. First, we've got an equation where we can look at the frequency of light, which is this V-type symbol, and this is equal to the speed of light over the wavelength of light. So we can look at frequency of lights in a lot of different aspects, whether or not that frequency of light's being absorbed or emitted from a molecule. And we can actually relate this to energy using this equation, where energy equals Planck's constant times frequency. So if you remember back to general chemistry, we use Planck's constant quite a bit, this H value, and this is equal to 6.62 times 10 to the negative 34th joules per second. So Planck's constant, so 6.626 times 10 to the negative 34th joules seconds. And so now we've got a direct way to look at the energy being absorbed and emitted. And this is the really useful part of spectroscopy, is we can start studying the quantum behavior of molecules, or the amount of energy that can be absorbed or released. So if we look at the electromagnetic spectrum here, we've got a bunch of different types of electromagnetic radiation that can be observed. If we look at what we typically see, we normally are looking directly at the visible wavelength. These are things, are waves between 400 and 700 nanometers typically. There's actually a really interesting radio lab talking about how there are some people that can actually see a little bit further into the IR region because they have a special receptor in their eyes. Conversely, there are some animals that can see higher frequency light all the way up in the UV. So this is kind of the range that most animals can see within. We're really limited with what we can see with our eyes, and we're stuck in the visible range. If you go to higher frequencies, you can use X-rays, and this is actually used to study the absolute structure of organic and inorganic molecules. And then if you go into nuclear chemistry, you'll study gamma rays, which are very high energy rays that can go through most objects. If we go to the other end of the electromagnetic spectrum, we run into thermal IR. This is our body heat. It's any sort of heat that's being emitted as an electromagnetic radiation. If we go further, we run into microwaves, which we can use to transmit information or even cook our food. We go further into radar, and then we go down into radio and TV waves, which are broken down further into UHF and VHF TV signals, and then FM and AM frequencies. AM frequencies are very, very long, which allows them to travel very high distances. So chemists use a variety of these different types of radiation to study the behavior of molecules. One that we recently covered in lab was UV vis. So we said with UV vis, what we're doing is studying the electronic excitation of molecules. So we said if you've got some sort of ground state, so ground state, there's some vacant orbital above it, and what we're really doing is we can study this orbital, this antibonding orbital that's higher energy, by exciting one of these electrons up into it using UV or visible light, and then seeing what frequencies of light are absorbed. IR, if we look at that, is looking particularly at bond vibration. So typically the bond vibration occurs in a couple different manners. You generally have bending or stretching. These are the two types of spectroscopy we've already used in lab. We're not going to get into microwave spectroscopy, but you can use microwaves to actually study how molecules rotate. And later on in the term, we're going to use radio waves to actually study nuclear spins. And so this is where the concept of NMR, or nuclear magnetic resonance spectroscopy comes in. So generally what happens is you've got some matter here, right? And this matter, let me actually change colors, sorry. Let's say we've got our matter. This matter is at its ground state. That's not to say that it isn't excited to some extent. Every molecule has motion because it's not an absolute zero. But what we do is we take an additional energy packet in the form of electromagnetic radiation, and what we do is we take that matter and we put it into an excited state. This excited state is usually designated with a star, at least when we use molecular orbital theory, and this excited state is somewhat unstable, so it wants to release energy and go back down to the ground state. And so this will release another energy packet back out. And the question is, well, what is this energy that's released back out? It's usually not the exact same energy packet that's put in. It's actually a little bit different. And depending on the frequency of the electromagnetic radiation input, we can get heat coming out of a molecule, as in the case of a microwave. You can heat up your food. You can get light. So with fluorescent molecules, when you excite them with the UV light, you can actually see them glow under a black light. You can see molecular rotation occur, as in the case with microwave spectroscopy. You can see vibration, as in the case with IR spectroscopy. There's actually quite a few other types of energies. So really with spectroscopy, all we're doing is we're studying the energy that's either absorbed in the first step or emitted in that transition from your excited state down to your ground state. All right, so let's delve a little bit into IR spectroscopy. With IR spectroscopy, you generally have some sort of IR source. There are a variety of different IR lamps that you can buy. And what these do is they emit frequencies of light that are all within that IR range. So we've got these different wavelengths, different packets of energy. What they do is they hit our sample there. So we've got some sample. In a lot of labs, what this is it's actually two salt plates, and in between it is a sandwiched organic compound. In our lab, we actually have a different sort of IR, but the same concept applies. What happens is much of this light is just transmitted through, right? So it just goes straight through the sample. It's fairly transparent. But at some frequencies, the light is absorbed, right? So at this frequency, the light was absorbed by the sample. The light was absorbed. And so we said that anytime IR light is absorbed, we're initiating some sort of vibration, right? So I think the easiest way of thinking about these vibrations is to relate it to springs, right? So covalent bonds are really similar to springs. Covalent bonds are like springs. And if we think about a spring, we can do a lot of things with it, right? So let's imagine we've got a spring with two weights on the end. And got my second weight there. If we want, we can apply energy to it, right? And we can stretch this spring out. So we've taken it from its ground state, the normal spring in its relaxed state, and we've excited it all the way up to its stretched out state. So this is analogous to the excited state in IR spectroscopy. If we think about a covalent bond, it's a little abstract to think about, but what we can think of is, let's take ethane, for example. And I'm not going to draw the orbitals for the hydrogens. I'm just going to draw the orbitals for the carbon-carbon sp3 overlap. So we've got an sp3 lobe here, and we've got another sp3 lobe. Oh, that's a little big. Another sp3 lobe there. And again, we can take this energy and we can say, well, what happens if we take these two carbons and we stretch them apart from one another by exciting it with light? And really, it doesn't look too exciting from the molecular orbital level, or overlap level, but essentially what happens is you can perturb that orbital so that it becomes more stretched out, just like the spring. And when this happens, you have a non-optimal overlap. You can do this two ways. You can either stretch it by pulling them apart or bend them out of plane in some way so that you're getting a bending sort of vibration. So we've got two main modes of vibration. So two main modes of vibration, or I'll call it excitation. We can either stretch, as in the example where we're looking at the spring above, or we can bend. Both of these are analogous to springs, right? So we could take a spring and we can bend it, or we can stretch it. And with bending, there's actually a couple more modes of vibration. You can have in-plane bending, or you can have out of plane. So you can imagine if you stick your arms up like you're going to a Y, you can have your arms go out. So essentially they stay in plane with your body or your chest, or you can have an out of plane bending where one arm twists in front of you, the other arm twists in back. There's a bunch of different types of in plane and out of plane vibration. It's just looking at different types of frequency that can be absorbed. Molecules can vibrate a bunch of different ways, and we see all those excitations in the IR spectrum. This can all be explained pretty simply by using the concepts that you may have learned in physics, specifically with Hooke's law. And Hooke's law wasn't really looking at covalent bonds, but the same idea applies because we said that covalent bonds are like springs, right? So vibrations depend on three features. Depend on three features. The first feature is the mass of the two objects. Right, so if we think about our spring example that we had above, if you take one of these masses and you pull it up and you hold the other one stationary, and that's a really, really heavy mass on this blue atom, will it go fast or will it go slow? Well, we know with heavy atoms that the frequency will actually be lower, right? Frequency is lower with heavy atoms. Conversely, the frequency is higher with light atoms. So if we go back to our spring analogy, if that blue atom right here, if that's nice and light and we pull it up, it's going to vibrate very, very quickly and go back down to the ground state very quickly too. So that's one feature we have to pay attention to. The other feature is looking just simply at the strength of the spring or the bond. if we've got a bond that's very, very strong, it's going to cause the spring more or less to act like a stronger spring, and it's going to vibrate at a higher frequency. So frequency is higher with strong bonds. And conversely, the frequency is lower with weaker bonds. All right, and then the very last one is actually looking at the length of the bonds, or the length of our spring. Length of the spring or bond. So if we think about this, if we've got a really, really big, long spring, the frequency is going to be lower. So frequency is lower with longer bonds. And the frequency is higher with shorter bonds. And really the example that I use to clarify this is, well, what do I mean by longer and shorter bonds? How does that deviate from stronger and weaker bonds? The two are very closely related, but with this one we can think about the sp3 versus sp2 versus sp orbital, right? If we look at it, which one's going to be longest? Well, it's going to be our sp3 orbital, right? Because it's got the most p characters. So this will be our longest bonding orbital, and then sp will be our shortest. So for example, if you have a hydrogen that's bonded to a carbon that's sp3 hybridized, that carbon-hydrogen bond is going to be much, much longer than a hydrogen that's bonded to an sp hybridized carbon. All right, so if we look at our IR spectra, we've got a bunch of different features we can look at. The first one that is really easy to look at is just our wave number, right? And wave number is just a fancy way of saying frequency. R-E-Q-U-E-N-C-Y. And so wave numbers, which we said is a fancy word for frequency, is measured in inverse centimeters. So we do centimeter with a -1 as the exponent. And then we said that higher frequency is indicative of either a light atom. It can be indicative of a strong bond. Oh man, there's a cat here. Or it can be indicative of a... Oh my gosh, I'm going to stop these cats. Sorry. Alright, sorry about that. I had to deal with the cat situation. So we said that frequency can be indicative of a light atom that's vibrating. It can be indicative of a very strong bond, or it can be indicative of a very short bond. So we've gained a lot of information from the positioning here. Conversely, we said that the lower frequency is indicative of a heavy atom vibrating, a weak bond, or a long bond. So it could be one of these three things. And there are two different charts that I gave you guys in class. If you don't have one with you, you can pull them up online. This first one I actually found on a website called Compound Chemistry. And with Compound Chemistry, the guy is a graphic designer, and he's already laid it out really nicely for you. So if you look at the bottom part, he's got our absorption in inverse centimeters, right? So this is our frequency. We know that as we go right, that it's a higher frequency. Or sorry, excuse me, if we go left, it's a higher frequency. If we go right, it's a lower frequency. So I told you guys already that if we're looking at a normal alkane stretch, that sp3 hydrogen stretch, it's right here. And then if we think about, all right, well, what about alkenes where it's an sp2 hydrogen stretch? That's a shorter bond, so it's showing up as a higher frequency. And with our alkynes, you can actually see them a little bit higher because that's an sp3 hydrogen overlap, so it's an even shorter bond. If we think about heavy versus light atoms, the very, very heavy atoms are the halogens, so they show up at a lower frequency right here. If we think about bond strength, oftentimes the weaker bonds are down here, so we know that we can do halogen abstraction pretty easily. So halogen carbon bonds are oftentimes very weak. That's what makes them good leaving groups. So this chart kind of lays it out in a very visually pleasing way. If you are ever looking at your IR chart or IR spectrum, you can try to match it up with this chart and say, well, I've got a peak in this region. What could it be? And you could say, well, it's probably an aldehyde, ketone, an amide, an ester, an acyl chloride, an anhydride, an acid, just some sort of carbonyl group is really what it boils down to. And so from here, you can keep on troubleshooting and then use more evidence to try to deduce what your compound might be. So this is a really nice chart to use. Another chart that I gave you guys, I handed out in the first term portion of the lab, and it lists all of the different functional groups. It has a really nice layout. If you look on the left, or sorry, the right, the intensity, so M equals medium intensity, S equals strong, and W equals weak. You can use this chart to really try to narrow down the functional groups. So one thing that I will say is that this is a simplified chart, right? This isn't all-inclusive. There are always exceptions to everything. So not absolute. There are different features in molecules that may change your frequencies to be a little bit different from these, but in general this is a really good guide to use. One other thing I will tell you guys is typically below about 1,000. I call this whole region over here the fingerprint region. And the reason this is called the fingerprint region is that it's not really that useful interpretively because there's so much going on in it. There are a ton of CH bends and stretches that go on there. And oftentimes it looks like grass. It's very hard to interpret. But what it is useful for is matching spectra. So if you've got a spectrum that you took and you found a literature one online, you can literally overlay them and the fingerprint region should match. Just like police use fingerprint identification to find suspects or try to find somebody. Exact same sort of concept here. So we can use wavelength really, really easily to help identify structures and various molecular features within molecules, or even deduce what our compound is. There's one more thing that we've always got to watch out for, and that is resonance. Watch out for resonance effects. And I'll give you guys an example that might make a little bit of sense. So let's take this ketone. If we take this ketone, we can draw a resonance structure for it, right? So we can say, all right, let's move that lone pair up to this oxygen. So we've got a nice resonance structure there, right? So if we look at that carbon-oxygen bond, it's not a true carbon-oxygen bond, or a double bond at least. It's a carbon-oxygen between a single and double bond. So if we look at this bond shows up on an IR spectrum around 1720 inverse centimeters. All right, let's take another example. Let's say we've got a very, very similar ketone. This one's an alpha beta unsaturated ketone. If we try to do the same thing, we can say, all right, so let's move those electrons up. We know that it's not quite a double bond. It's actually a little bit more like a single bond than we would initially think. Now this carbon's got a positive. Whoops, I forgot my positive up there. And then we have one more resonance structure where this double bond can actually go over and delocalize. When we look at this structure, we've moved the double bond there. This oxygen still has a negative charge. This carbon has a positive. And you can say, all right, now there's 3 resonance structures. So if we look at this bond is more single bond like, right? Because we've got 2 resonance structures where it's shown as a single bond, where if we look at this one right here, this bond is less single bond like. So if we think about where these should show up in the IR, this one has more single bond like character, which conversely means it'll show up at a lower frequency. Right? Because we know that single bonds are weaker than double bonds. So we've always got to watch out for these resonance effects. So typically the key hint to whether or not you have a resonance effect is if you have some sort of double bond next to a carbonyl group. So these are called alpha beta unsaturated carbonyl groups, or ketones, aldehydes, etc. These will be shifted from what's shown on the chart up here. So really watch out for resonance. Oftentimes I have students trying to interpret IRs and they say, well, we should have made a ketone, but it's showing up at 1675. It's not between 1725 and 1705. And then I have to remind them, well, they take into account resonance, and oftentimes it's something that kind of flies under the radar for a while. So you've always got to watch out for resonance and not use this as a definitive source of what functional groups should show up as. All right, there's some other features that are really useful for IR as well. One of them is signal intensity. And so if we look at the chart that I gave you guys, I've got a list of signal intensities in that right-hand column. This list is actually fairly useful, right? So the reason they're useful is that dipoles actually act like little antennas. And they absorb IR light really well. So going along with this, more polar bonds are more intense. That's really the take-home picture. I'm not going to get into the physics behind it, but if we go back to our chart, we can see that this idea applies, right? So our most polar bonds are probably going to be things like our carbon-oxygen bonds. Our carbon-oxygen bonds always show up as strong in that right-hand column. If we look at our other carbon-oxygen bond, it also shows up as strong. If we look at our sulfoxides, for example, where we've got a sulfur-oxygen bond, again, these all show up really strongly as well. Same with the halogen bonds, because there's such a big dipole there. They act like little antennas and they absorb IR light really well. If we look at some of them where they're not that polar, maybe something like, let's see, one of these weak aldehyde bonds, there's not a lot of polarity difference between carbon and hydrogens. So these typically show up medium or weak, depending on the type of frequency that we're observing. All right, so there's one other one besides signal intensity, and that is signal shape. So if we think back to our labs, we know that we can determine a lot about the shapes of molecules, right? Specifically, we've got broad shapes. So if our peak is really broad, meaning that if we look at our IR, we've got some sort of blob in it, kind of like that, that's typically indicative of some sort of hydrogen bonding. So that's a really useful one. And then a narrow shape, means that there's little or no hydrogen bonding. The two to really watch out for are alcohols and amines, right? And I'm going to break amines into two categories. So we can have our primary amines, and we can have our secondary amines where one of those hydrogens is replaced by some other group, right? If we look at these are very broad. And if we go back to our chart and we check where they should show up, we see that alcohols will actually show up a little bit differently depending on whether or not they're free or H-bonded. You may see both of them, but they typically show up around 3,500. So we'll go down and we'll say you show up around 3,500 inverse centimeters. And if we look at our means, there are two peaks. We've got two hydrogens, which is a really useful diagnostic tool, and they are less broad. And if we think about, well, why are they less broad? Well, we know oxygen's more electronegative than hydrogen, so the hydrogen bonding capability of an amine is a little bit weaker than with an alcohol. And if we look at a secondary amine, we only get one peak, and it is also less broad. And if we again go back up to our chart and we ask ourselves, well, where should amines show up? We've got primary and secondary amines. If we're looking in that same region, typically where hydrogen bonding is very apparent, it's going to be also around 3,500 to 3,100. So we'll say 3,500 to 3,100 inverse centimeters. So these are really useful diagnostic tools. So what I typically do is I develop a strategy when I get an IR spectrum, especially with an unknown compound. And the strategy goes a little bit like this. The first thing I do is I look for H-bonds, or hydrogen bonds, right? They just kind of stick out like a sore thumb, so alcohols, amines, things like that. You can spot really quickly. So alcohols, amines, phenols, or carboxylic acids. These you can spot really quickly. The other thing that I do, which is step 2, is I look for carbonyls, right? So look for CO peaks between usually 1640 to 1760 inverse centimeters. They all show up within there. And this can help you narrow down your potential functional group. So for example, you may immediately rule out, hey, this isn't going to be an acid halide, it's probably going to be something like an aldehyde or a ketone or something like that. Again, you've always got to watch out for resonance. All right, the third step in my strategy is that I draw a line at 3,000. Essentially, if you draw a line at 3,000, and let's say we've got 3,000 3,000 inverse centimeters down here, and then we've got all the way down to 400 centimeters over here, and then up to 4,000 over here. We can break these down based on the 3,000 centimeter line. Essentially, the really useful tool is that if we go to the right side of it, right near 3,000, these are going to be sp3h bonds. Right? So we said if we've got a carbon that's sp3 hybridized, it's a longer bond, it's going to vibrate at a lower frequency. If we look at the sp2 hydrogen bond, it'll be right above 3,000 inverse centimeters. And if we look even right of that, we can run into our SPH. So we can immediately look at how saturated our compound is. If it's unsaturated in some way, we will see peaks that show up in this region, whether or not it's an alkene or an alkyne. Obviously, if we're thinking about an SPH overlap, this is very indicative of a terminal alkyne, so that can be very useful as well. So this gives you some idea what's going on. The very last thing that I look at is you just want to look for other strong features. Oftentimes with things like esters and other functional groups that have a carbon-oxygen single bond, those stick out really well. The one thing I will caution you to do is to ignore anything below 1,000. I've had students before where they say, well, I've got a really strong peak. It's showing up where the halides should show up. I'm confident that my compound has a halogen on it. Well, not always. There can be a lot of other strong peaks in there, so don't really rely on anything below 1,000 too much. All right, so the last thing I was going to have us do is quickly go through some practice problems and see some real-world examples of what's going on here. So here's an IR practice problem from our book where it says we've got a compound with a molecular formula of C6H10O that gives the following IR spectrum, and it specifically gives a wave number at 1720 and 1650. So we can look for H-bonding features. That was number 1 in my list. Are there any H-bond features? If we look at our chart, H-bond features should have been somewhere in this region. There's really no big broad peaks there, right? So immediately we can say, well, there can't be this guy or that guy in there, right? All right, so we've gained some progress. We've ruled 2 out. That's very good. All right, the next thing we said to do in our strategy list was identify CO features between 1640 and 1760. Well, we've got one there, right at 1720. So if we think about what shows up at 1720, we can go back to our chart. You can say, all right, 1720, what could this be? What could this be? Well, it could be, I'll highlight them in green. It could be an aldehyde, could be a ketone, could be a carboxylic acid, could be an ester, probably not going to be an amide because that's shifted way too low. It's probably not going to be an anhydride, and it's probably not going to be an acid chloride. So we've narrowed it down to an aldehyde, ketone, carboxylic acid, or ester. But we can rule one of these out already, right? We know it's not going to be a carboxylic acid because we haven't seen the CO stretch. So it's going to be an aldehyde, ketone, or an ester. So let's go back and look at it. We know it's not going to be that. It's not going to be that. It's not going to be that. So we've already ruled out 3 more. We've got an aldehyde and 2 ketones. The other thing we can look at is say, okay, well, if it's an aldehyde, we should see this peak right here, right? This CH peak. So let's go see where that shows up in our IR handout. If we look at our aldehyde CH, we should get 2 signals, one between, I don't know, around 2800 and one right below that. So generally they show up as a pair. So let's go back to our chart. If we go 25, 26, 27, 28, I don't really see a pair of peaks there. So you can say it's probably not going to be our aldehyde. Now we're running into a situation there, right? So we've got two different potential compounds. We know it's either going to be this one or this one. So we've got to ask ourselves, okay, which one could it be? Well, if we look at this one's got resonance features, so it should show up at a lower frequency than a normal ketone. In this case, if we go back and look at our charts, 1720 was right in there. So evidence is pointing to the fact that this is just a normal ketone, not some sort of alpha-beta unsaturated ketone. So I would say if we use all of our data here, we can cross this one out and we can say, all right, it's got to be that one, because if we had this alkene right next to our ketone, the ketone should show up at a lower frequency. The other thing we can do, we kind of skipped, was draw our line at 3000. We've got peaks indicating unsaturation there. We've also got carbon-carbon double bond peaks showing up around 1650. So all of this indicates that we've got some sort of alkene, and our carbonyl frequency indicates that it's not going to be an alpha beta unsaturated ketone. Or it's not going to be an alpha beta unsaturated ketone. So it requires a fair amount of detective work. Oftentimes the strategy I gave you has limitations, and you've got to do more problem solving, but it's a good start. All right, let's do the next one really quick. All right, let's first look at our alcohol ones. So we've got one where it's just an alcohol here. Let's see if we have any alcohol features. Well, I'd say, wow, this has got to be an alcohol feature. And this one's got to be an alcohol feature. If we go back and we look at this one should also have a CO double bond stretch. Looks like this one also has a CO double bond stretch. So we can say, all right, this one's got to be this carboxylic acid stretch. Really nothing else makes sense. Conversely, if we look at this one, we can say, all right, this one's probably going to be our alcohol. So just by using the alcohols, we've already identified two of them. We had to rely a little bit on our carbonyl stretches, but it worked out pretty well. So let's cross these out and then go from there. All right, what's the next next best identifying functional group? I would say let's look for an ester here, right? So we know esters, go back to our chart. Esters show up between 1750 and 1730, assuming there's no resonance, right? So which one has one between 1750 and 1730? I'd say that one right there. If we look at any of the other ones, yeah, there's not really a strong peak there, so nothing there. If you look at the one below it, same thing. If you look at this one down here, it's a pretty weak peak. It's not a strong peak, so it looks like our ester is probably going to be this one. So we'll fill this in. And we'll cross it out. Now, if we go back, we can say, all right, which one has a functional group that stands out? Well, this one's a secondary amine, so what about that? It should show up in that hydrogen bonding region, but it's not as intense. And it should have a pair of peaks. Well, there we go. We've already identified our amine, right? So let's go through and draw our amine in. So we've identified our amine based on that primary amine set that shows up in the hydrogen bonding region. Now we've narrowed it down to the last two. So we've got an alkene here, right? So if we draw our line at 3000, it's about right there. I know my hands are kind of shaky, so I'll do my best here. This one has an sp2 hydrogen peak, so I'd say this is pretty indicative of our alkene. And if we look at the other one, it's indicative of our regular alkane. So this is kind of the thought process I go through when I'm trying to identify our features, and I would recommend you guys go through the book, try to work on this a little bit. We're going to be using IR, usually in tandem with a couple other different forms of spectroscopy for the remainder of the chapter, but it's a good idea to brush up on your IR because it's a very valuable tool to have. All right, thanks for watching.